So what I'd like to do on this section of the video is do a demonstration of what a VNG test, or a video nystagmographic test, would look like and how we do it in our office. I'm here with Donna and one of our patients. Donna is one of our VNG techs, and today what she's going to do is she's going to demonstrate how the VNG is performed. So Donna, if you don't mind, show us the goggles if you would. So what VNG is performed with infrared goggles, and what these infrared goggles have is little mini cameras in here that will measure eye movements, or what is known as ocular motility. So these goggles are very gently placed on patient's head over their eyes, and what will happen is the patient will be able to look through the goggles, and there is infrared camera again within the goggles, within that glass of the goggles, and what will happen, and we'll show this in a moment, is the stimulus will be on this TV here, and what will happen is various types of eye movements will be measured. Now, some of you with vertigo or dizziness or balance disorders may have been to your EENT, and your ears, nose, and throat doctor may have performed a test similar to this. Typically the test that they do, they use the same equipment, but the test that they do is more to look at inner ear function. Although they may be able to look at abnormalities in brain function, they typically are not trained to diagnose those and treat those. So we use the same type of testing procedures, however we look at it more from a neurological perspective. And some of you may have been to your ENT and have had something called a caloric. A caloric is when they put warm or cold air into your ear, and that can create vertigo and things of that nature. I want you to rest assured that in our office we don't use that unless we really believe that there's an inner ear problem. So typically we just use the neurological components for the VNG. So the first test that we run with our VNG protocols is the gaze testing. And if you look closely on the screen, there is a dot, and what basically will happen is the patient will be instructed to look at the dot for a period of time as the computer measures gaze stability, or the ability to have proper gaze. So this dot is right now in the center portion, and we also measure various other gazes. We'll look at gaze up, gaze down, gaze left, gaze right. And people typically with balance disorders or vertigo or various neurological disorders such as concussion, a lot of times will have poor gaze stability, and poor gaze stability can affect their balance, it can affect the way they feel in their head, it can create all types of neurological disorders. So now what I'd like to do is show you some examples of what the gaze testing looks like and what the gaze printouts look like on the VNG. Okay, now this is an example of gaze testing in our office. So when we do VNG, what we do is we look at a patient's gaze, and what they'll do is, of course, you just noticed it and just watched it, they stare at that dot. It's essential for the eyes to remain very stable, and when people get into head injury or if they have degenerative disorders, they can develop instability in their gaze or jerkiness in their eye movements, which can affect their balance. It can affect a lot of different things. So when we look at these here, what we like to see is we like to see a very nice printout that is basically straight across, meaning that the eyes are not jerky at all. So it should be like a flat line baseline. And then what we also get with this is we also get the eye movements. So we can look at the eye movements, and the eye movements, when we do gaze, the eyes shouldn't move at all. So if we play this, we can actually play the video. This person's eyes are relatively stable. They're staying completely still, and they're not moving at all. And so that's exactly what we like to see in our testing with gaze. This would be a normal. If we look at somebody to the gaze, we test them to the center, to the right. Here's the right function, and if we look, we can see a nice printout, very nice straight line. Okay, but if we look here, he moves his eyes to the right. There is no movement, and in this person, this was a normal subject without any neurodegenerative aspects going on, or head injury or anything of that nature. We can also look at the size of the pupils. They should be even from side to side. And these are some of the things that we can look at with gaze. Now this patient here is a patient that had a concussion, a head injury. And in this specific test, we are looking at gaze to the left. And if you look here, and I'll zoom in so we can see a little bit better, the printout, you can see that this here is the left and this is the right eye. And if you see, it should be smooth, but you see these little square things in here. These are called square wave jerks, and they're very common in people who have had a head injury. It's a failure of a certain part of the brainstem that is not allowing the eyes to remain steady, and we want a nice steady gaze. So we'll show you what this looks like. Again, this is gaze to the left. This is a concussion patient. Now watch the eyes. When we hit they're not stable. You'll see that jerkiness. That's an involuntary jerk. This patient is trying to look at the target and their eyes are bouncing all over the place, which can create a variety of issues and problems. Here's another example of gaze testing. This is gaze to the left. This is a patient that has a balance disorder and what we call ataxia, trouble walking and dizziness. You can see up and through here still a lot of right square wave jerks. This is a separate patient. We can watch the video of this individual. You'll see just small jerkiness in the eye. Again, that can be really tough for a patient to walk when they have this jerkiness in their eyes, or it can also make their balance. I mean, this patient can walk, but they just are not able to ambulate as well as they would like. But so that is gaze to the left. However, if we move to this person gaze center, much better, still some jerkiness, but much better than gaze left. So some people will have a problem in one direction of gaze and not a problem in another direction of gaze. This is something that we want to determine, because when we create our therapeutic strategies to help a person, we need to know where they're good and where they're bad. Here is another example of a different patient. This guy has a balance disorder. And if we look in, we can see some very small jerky motions. These are smaller, more frequent jerks, or jerky, or what we call square wave movements. And if we look at this person's eyes, you'll be able to see it. His eyes are moving around. You see that jerkiness back and forth. We don't like to see that. That is something that we see in head injury. We see that in various neurological disorders. And one more example. This is a very common thing that we see. You can see the jerkiness in this person's eyes. This is what we call nystagmus, and it's an upbeat nystagmus. Nystagmus means there's like an asymmetry in the way the brain is functioning, especially in the brainstem area. And we can see this in this patient, and this is in gaze testing, and the gaze testing that we do in the dark. So watch his eyes carefully. See that beating up? That's what we call nystagmus. So this is something that we see. This patient is dealing with dizziness and these types of aspects. So we can help patients with these types of things if we develop specific therapeutic strategies. So that's all for gaze. Let's now move on to pursuits. The next test we're going to demonstrate on the VNG is the pursuit mechanism. And pursuits are a slow, consistent movement of your eyes from side to side, either horizontal or back and forth. So basically what's happening is the patient will look at this dot as it goes back and forth, and we can measure the smoothness of a person's pursuits. And then of course that will be printed out and it will be recorded on the computer of the VNG. So this is exactly what the patient is going through. And what will happen as they do the pursuits, the ball will start to move faster and faster and faster. In fact, we do 1 hertz, 2 hertz, and 4 hertz. Okay, now we're going to go over pursuits. Pursuits are, again, you just saw it when the eyes it will track something back and forth. And so when we look at this graph here, and I'll zoom in so we can see this, basically the downward movement is to the left, the upward movement is when the ball goes to the right, down is left, up is right, and so on and so forth. And so with this, we should see that the patient follows the ball with a pursuit mechanism, so they stay right on, so that and you may not be able to see the color, but the blue is normal, the green is the patient, and anything that's off is the red. So this is a normal patient. As he did this test, as this person did this test, he stayed right on the target. And so this is the smoothness of these eyes, if you'd like to take a look. And so this is nice, smooth pursuit mechanism going back and forth with no issues. That's a healthy pursuit mechanism, which means certain parts of the brain, mainly the parietal lobe, is functioning very well. So that's normal. And then we can do these at different speeds. So we do this at 1 hertz, 2 hertz, and 4 hertz, which you took a look at when we went over the pursuit demonstration. Now, in this patient, again, this is horizontal pursuits. This is a concussion patient, and you can see as we look here, going to the right, fairly smooth, a little jerkiness here. We get what we call a leftward square wave jerk here, and we come up, pretty smooth, but then to the left, another leftward square wave jerk, another leftward square wave jerk. And as we move up even further, pretty good to the right. As we go down, which is left, leftward square wave jerk, and so on and so forth. So this patient has square wave or jerkiness in their pursuits when they go to the left. Again, this patient had a concussion. And if we come down, we'll go over this with the eyes. So this is what it looks like. And so here's the patient. She's gone to the right fairly smoothly, and then she moves to the left and pretty smooth there. But as she does it more, pretty good here, and then she starts going to the left, jerkiness. Not smooth there. Fairly smooth to the right, and then right there, not smooth. That is a leftward square wave jerk to the left, and that is a left brain, left parietal lobe problem, and that's something that we see again in concussion cases. Here is a patient with, again, doing horizontal pursuits at 0.1 hertz, and if you can see, this is where they should be. So this particular individual is unable to even stay on the target. He's either ahead or behind the target, and it requires him to make these jerky eye movements to get back to the target. So as you can see, that's not what we like to see. This patient again has a balance disorder and chronic pain, and if you look in here, bounciness, jerkiness, 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 and if we take a look at what that looks like with his eyes, let's look. You can see a lot of bouncing to the movements. It's not smooth as it should be. There is a lot of bouncing in there as well. And we get to see it pretty intensely here. And then we move in here. So that would not be what we'd like to see in a patient with pursuits. That would be some dysfunction of the pursuit mechanism. Here's another example of a pursuit mechanism. Now these are vertical pursuits. So up top here you're looking at the horizontal aspect of eye movements, and in through here you're looking at the vertical. So this is up, down. Vertical means up and down, up and down. And if we look in here, if we get a little closer, you can see that not very stable and not so good in the vertical aspect. But then as we go and we look at the horizontal aspect, not so good there either, because as we look, there is like a jerkiness all through here. You see all these jerks in the horizontal. So this guy's supposed to be only going up and down, and not only is he going up and down, he's going up and down and side to side when he shouldn't be doing that. So if we look at what's happening with the eyes here, we can take a look at this. So again, this guy has problems with balance, and he gets a lot of vertigo, and he also has some pain. So here's these eyes going up and down, but you see his eyes, as they go up and down, they're also going side to side, which is the horizontal movement. And so he should not have any horizontal movements while he's doing vertical movements, because the ball is only going up and down, it's not going side to side. So this guy has problems with stability in the horizontal plane as he's going up and down. So that can create a lot of problems with feelings of disequilibrium and feelings of poor balance and issues of that nature. And we can directly link this back to areas of the brain that we can stimulate with various neurological exercises and eye exercises to help this person. Our next test that we do in the VNG is fast eye movements. We do them horizontal and vertical. They are known as saccades, and Donna's going to demonstrate those right now.
Okay, and you're going to keep your eye on the dot.
And so they're randomized. So what will happen is the dot will move back and forth, and what we will be measuring and looking at is the quality of the saccadic movement, or the fast eye movement. Is it accurate? Is it fast? Does it take a while to take off, or we look at the reaction time. Patients that have concussion will have slow reaction time. Patients with things like Alzheimer's and balance disorders will have slow reaction time. So this is one of the other tests that we look at. Now let's look at some Saccade VNG graphing. So this is the printout for the Saccade testing, and basically, as you remember from looking at the Saccade demonstration, saccades are fast eye movements moving from right to left, and these are randomized movements. So if we look at what's happening here, this is what the printout or the video of the eyes look like during saccades. So we've got movements of the eyes back and forth, and we're looking at how metric or how accurate they are at hitting the target. We're also looking at the speed, we're looking at their latency, and we measure saccades not only with the VNG, but we also measure them with the saccadometer. So essentially, if we look at this printout here, this is an example of a very normal and good-looking saccade test. So basically what happens is the top one is the left eye and the bottom one is the right eye, but we'll just look at the right eye here, and we'll kind of zoom in on it a little bit more. But when the dot, as we come here, as the dot appears to the right, that's up. And so this is that stimulus, that dot, and then what happens here is this is how long, or the latency that it takes for that patient to move their eyes there, and then do they land right on the target, which this person lands nice and square on the target, and then as they're staring at that dot on the right side, how stable are their eyes after that eye movement. And then now this is a saccade or an eye movement back down to the left, and then we come up here to the right, and these are nice, they should be nice and square and then nice and smooth. This one here has a little undershoot, so you can see that means that they're not hitting it exactly on target, but for the most part this is a pretty healthy looking saccade test on the VNG. Now this saccade printout on the VNG is an example of somebody who has some undershooting. So when this patient, and we'll zoom in so you can look a little bit more detailed, when this patient is saccading or moving their eyes down to the left, or moving them to the left, you can see that it should just be one square and down, but this one kind of stops, and then there's another little delay, and then back again. So this person is actually undershooting the target. So this person is not metric. This is a patient that has dizziness and some issues there. And then as you can see to the left again, he undershoots the target. And he does pretty good here to going up, which is to the right. And then a little bit of an undershoot in through here. So again, that's an example of undershoot, but he's very fairly stable between the saccade. So as he's actually stopping on the dot that he's looking at, he doesn't bounce around very much. So that's a good sign there. Now this patient is a patient with a concussion, and you can see here that when this person fast eye moves their eyes fast to the right, they do it okay here, but then in between, when they're supposed to be holding their eyes stable on that target, their eyes are bouncing all around. And then as we go, then they try to move their eyes down to the left, and they do this with a pretty big left undershoot. And then again, more jerkiness of the eyes. So this person cannot hold gaze very well. And this is the kind of things that we see with patients with various neurological disorders, whether they're from an injury or whether they're degenerative over time. But we don't like to see saccade testing that has all of this bounciness in between. And then here is a example of someone with, as they're moving their eyes to the left here, they do it in almost 3 steps instead of getting there in 1 step. So that's saccade testing, and I hope that'll make more sense to you when we go over your own films, not your own films, but your own VNG testing. Okay, and our last and final test is optokinetics, otherwise known as OPK, and essentially what's going to happen here is we're going to look at a visual surround. So basically these balls are going to move either to the right or to the left or up or down, and what will happen is the eyes of the patient will need to pursue them and then refixate back to the other. And so essentially this is a very important test that looks at brain function on the right side, the left side. It also looks at some of the generators that can be affected in the brainstem. And so what will happen is the patient's eyes will be following these, and so a very important test. And so let's go over some of the OPK graphs from the VNG. So this is what a normal OPK or optokinetic graphing would look like, and basically when the stimulus goes by, whether it's bars or little balls that go across the screen, what a patient's eyes will do is they will slowly track them and then they fast refixate. So these sort of bent lines here are the slow tracking, and then the ones that are sort of upright, which is to the right, this is a stimulus to the left, which is a left brain. So if this patient has a very healthy left brain because they've got a very good response to their optokinetics, it should look like a saw almost, or like a bread knife, and you should see it should be just like that, real jerky, and it should be nice and even all the way through. The frequency should be the same. And the amplitude, which is how tall the graphing is, should be pretty much even all the way through. So this is a normal, this would be somebody with very good brain function, at least to the left. This is optokinetic results from a teenager that suffers from ADHD, attention deficit disorder. And typically ADHD is a problem with the right brain, and if you look at this response, this is to the right, and it should have that sort of saw-like response like the normal just had that we went over, but this one here doesn't even kick in at all. In fact, it takes a while to kick in, and finally you get a little bit of a response, and then it goes flatline again, and then it kicks back in. So this would be an example of somebody with a deficient right brain, and it's interesting because you can compare other findings. Typically, when the brain is not firing so good on one side or one hemisphere, you'll get usually a larger pupil on that side. Not always, but usually. And you can see that this right pupil, this patient is actually facing us. This right pupil is larger. So we can correlate the optokinetic findings with all the other findings that we see in our neurological exam and in our advanced neurological testing. We'll see a larger pupil on the side of deficient brain. So we can correlate all of the findings from our exam, from our VNG findings, from our saccadometer findings, and we can come up with a specific type of neurological program to improve the areas of the brain that are not functioning well. Now, this is just one sort of way that OPK can be abnormal. There are hundreds of different ways. I'm not going to bore you with that on this video, but this is one. This is an example of one that's really not even getting. It's not going so well. It's not picking up the response.